clocks. One falls toward a black hole. The other watches from a safe distance. The falling clock ticks normally, second after second, steady, untroubled. The watching clock records the falling clock slowing down, stretching the interval between ticks until the gap becomes a year, a century, a millennium. The falling clock approaches the event horizon, the boundary beyond which nothing escapes. And the watching clock records a fact that defies intuition. The falling clock never reaches the horizon. It slows, it reddens, it fades. It approaches the boundary forever. It never arrives. The falling clock experiences none of this. It crosses the horizon in finite, measurable time. Nothing special happens at the boundary. The crossing is smooth. Both accounts are correct. Both are predicted by Einstein's general relativity. The paradox is not a failure of the theory, it is the theory. By the end of this video, you will understand the event horizon paradox and why two observers disagree about what happens at a black hole's boundary. You will examine the singularity, the information paradox, and the competing theories that attempt to resolve them. And you will follow the evidence to its rational conclusion. If you find value in explorations like this, in understanding the deep puzzles that keep physicists awake at night, consider subscribing to the channel, which helps these deep dives reach more curious minds. Now, let us begin. The story of the black hole begins with a single equation, solved by a man who would not live to see its implications understood. Carl Schwarzschild, born 1873, died 1916, German physicist, solved Einstein's field equations for a point mass in a vacuum in December 1915, barely a month after Einstein published General Relativity. Schwarzschild was serving on the Eastern Front of the First World War at the time. He was stationed in Russia, calculating artillery trajectories by day and solving the equations of spacetime by night. He sent the solution to Einstein in a letter. Einstein presented it to the Prussian Academy of Sciences on January 13, 1916. Schwarzschild died 4 months later of a disease contracted at the front. He was 42 years old. The solution he found describes the geometry of space-time around a spherically symmetric, non-rotating mass. It is called the Schwarzschild metric, and it contains a radius, the Schwarzschild radius, that defines the event horizon of a black hole. The equation R sub s equals 2gm over c squared. R sub s is the Schwarzschild radius, the size of the event horizon. G is Newton's gravitational constant, approximately 6.674 times 10 to the negative 11 cubic meters per kilogram per second squared. M is the mass of the object. C is the speed of light, approximately 299,792,458 meters per second, approximately 186,282 miles per second. The equation is deceptively simple. It says, for any mass m, there exists a radius at which the escape velocity equals the speed of light. Inside that radius, nothing escapes. Not light, not matter, not information. The radius depends only on the mass. For the Sun, The Schwarzschild radius is approximately 3.0 kilometers, approximately 1.9 miles. For the Earth, the Schwarzschild radius is approximately 8.9 millimeters, approximately 0.35 inches. For the supermassive black hole at the center of the galaxy Messier 87, imaged by the Event Horizon Telescope on April 10, 2019, the first direct image of a black hole's shadow ever produced, the Schwarzschild radius is approximately 39 billion kilometers, approximately 24 billion miles. That is larger than the orbit of Neptune. That is a sphere of no return wider than the outer boundary of our solar system, surrounding a mass of approximately 6.5 billion suns. Think about these numbers through an analogy. Picture the Earth, 12,742 kilometers in diameter, approximately 7,918 miles, a sphere of rock and iron and water and air that supports billions of conscious beings. Now, picture compressing the entire mass of the Earth into a sphere 8.9 millimeters across, smaller than a marble, smaller than a pea, smaller than a lentil. At that compression, the escape velocity at the surface equals the speed of light. Light itself cannot climb out. The Earth becomes a black hole. The same mass, the same gravity at a distance, an entirely different geometry of space-time at the surface. Now consider the Sun. Its Schwarzschild radius is 3.0 kilometers, roughly the length of a large airport runway. Compress a star 1.4 million kilometers in diameter, approximately 864,000 miles, a sphere that could contain 1.3 million Earths, into a ball the size of a small neighborhood, and it vanishes behind an event horizon. The gravitational pull at a distance remains exactly the same. The orbits of the planets do not change. The geometry of space-time, far from the black hole, is indistinguishable from the geometry around the original star. The difference is entirely local. At the Schwarzschild radius and below, space-time is curved so severely that all world lines point inward. There is no outward direction. Every path leads to the center. The Schwarzschild metric describes this geometry with mathematical precision, and it contains the paradox that gives this video its title. At the Schwarzschild radius, in Schwarzschild coordinates, the coordinate time, the time measured by a distant observer far from the gravitational field, goes to infinity. The distant observer records that it takes an infinite amount of coordinate time for anything to reach the event horizon. The object never arrives. It freezes at the boundary, growing redder, dimmer, fainter. Its light shifting from visible wavelengths to infrared, to microwave, to radio. Each photon climbing out of the gravitational well with less and less energy, stretching to longer and longer wavelengths, but never crossing. Picture what this looks like. A camera positioned at a safe distance, aimed at an astronaut falling toward a stellar mass black hole. The astronaut falls freely, accelerating under gravity. As the astronaut approaches the horizon, the camera records a strange transformation. The astronaut's movements slow. Not because the astronaut is moving slowly, the astronaut is accelerating, but because the photons carrying the astronaut's image are struggling to escape the gravitational field. Each successive photon is born deeper in the gravitational well and arrives at the camera with less energy and longer wavelength. The astronaut's suit shifts from white to yellow, from yellow to orange, from orange to deep red, from red to infrared, invisible to the human eye, detectable only by instruments. The image dims. The astronaut appears to hover at the horizon's edge, frozen in a final frame that grows fainter with each passing year, each passing century, each passing eon. The astronaut is still there, in the camera's record, forever approaching, never arriving. The infalling astronaut experiences something entirely different. The proper time, the time measured by the astronaut's own clock, remains finite. The astronaut crosses the horizon in a measurable, finite duration. The crossing is smooth. In a freely falling frame, the equivalence principle, Einstein's foundational insight that free fall is locally indistinguishable from floating in empty space, guarantees that the local physics at the horizon is normal. No forces, no barriers, no drama. The event horizon is not a wall. It is not a surface. It is a boundary defined by the geometry of space-time, a point of no return, beyond which the escape velocity exceeds the speed of light, and the astronaut does not feel it. The astronaut passes through and continues falling inward toward the center, where the singularity waits. This was not understood for decades after Schwarzschild's solution. When the metric was first published in 1916, the mathematical behavior at r equals r sub s, where certain terms in the metric diverged to infinity, was interpreted by many physicists, including Einstein himself, as a physical singularity, a real barrier, a place where the physics breaks down, a wall that cannot be crossed. Einstein argued for years that such concentrations of mass could not exist in nature. In a 1939 paper, he attempted to prove that gravitational collapse to a Schwarzschild radius was physically impossible. He was wrong, but the error persisted for decades. Arthur Eddington, born 1882, died 1944, English astronomer, the man who confirmed general relativity by measuring the deflection of starlight during the 1919 solar eclipse, introduced a coordinate transformation in 1924 that removed the apparent singularity at r equals r sub s. Howard Robertson, American mathematician, demonstrated in 1939 that the proper time for an infaller to cross the horizon is finite. Georges Lemaitre, Belgian priest and cosmologist, the originator of the Big Bang hypothesis, independently showed the same result. David Finkelstein, born 1929, died 2016, American physicist, made it explicit in 1958, publishing a short paper showing that the Schwarzschild radius is a one-way membrane. Causal influences, light, matter, information, can cross inward but never outward. The event horizon is not a physical singularity. It is a coordinate singularity, removable by a better choice of coordinates, and the space-time there is perfectly well behaved. What does it mean that physicists, including Einstein, spent 4 decades believing the event horizon was a physical barrier, when it was always a mathematical artifact of the coordinate system they chose. Think about this through an analogy. Picture a map of the Earth drawn in Mercator projection, the standard flat map used in most classrooms. On this map, Greenland appears roughly the same size as Africa. In reality, Africa is 14 times larger. The distortion is not in the Earth, it is in the map. The coordinates chosen by the cartographer stretch areas near the poles until they are unrecognizable. A navigator who trusted the Mercator map absolutely would conclude that sailing to the North Pole requires covering infinite distance, because the map stretches distances there toward infinity. A navigator who used a globe, a better coordinate system, would see no such distortion. The Schwarzschild coordinates are the Mercator projection of space-time near a black hole. The event horizon is the North Pole. The apparent singularity is the cartographic distortion. The Eddington-Finkelstein coordinates are the globe. The true singularity, the physical singularity, lies at the center, r equals 0. Roger Penrose, born 1931, British mathematician, Nobel Prize 2020, proved in 1965 that under general conditions, reasonable energy conditions and the existence of a trapped surface, gravitational collapse inevitably produces a space-time singularity. The Penrose singularity theorem establishes that once a trapped surface forms, once matter has collapsed past the point of no return, the laws of general relativity guarantee that space-time curvature becomes infinite at some point in the interior. The infaller, having crossed the horizon, is carried inexorably toward this point. The journey from horizon to singularity takes a finite amount of proper time. A fraction of a second for a stellar mass black hole, hours for a supermassive one. At the singularity, the known laws of physics cease to apply. Curvature is infinite. Tidal forces are infinite. Space-time itself, as described by general relativity, ends. What does it mean that the most successful theory of gravity, a theory confirmed by gravitational wave detections, by black hole imaging, by a century of precision tests, predicts its own breakdown at the center of every black hole? Inside the event horizon, something even more counterintuitive occurs. Something so alien to everyday experience that no analogy captures it fully. In the Schwarzschild metric, inside r equals r sub s, the roles of space and time exchange. The radial coordinate r, which outside the horizon describes a spatial direction, you can move toward or away from the black hole, becomes time-like inside the horizon. The time coordinate, t, which outside the horizon describes the flow of time, becomes space-like. This means that inside the horizon, moving to smaller r is not a spatial motion. It is the passage of time. The singularity at r equals 0 does not lie at a point in space that you could, in principle, avoid by moving sideways. The singularity lies in the future. It is a moment in time, a moment that every infaller will reach, as inevitably as you will reach tomorrow. You cannot avoid the singularity for the same reason you cannot avoid tomorrow. It is not a place. It is the future. Think about this through an analogy, though the analogy, like all analogies for this concept, is imperfect. Picture a conveyor belt. Outside the event horizon, you stand beside the conveyor belt. You can step on it or off it. You can move left or right along the floor. You have spatial freedom. Inside the event horizon, you are welded to the belt. The belt moves forward. Forward is not a direction in space. It is the direction of time. The belt carries you toward the singularity, and you cannot step off because stepping off would require moving backward in time. The belt does not care about your wishes. The belt does not respond to your engines, your rockets, your frantic attempts to reverse course. Even light, the fastest possible motion, cannot escape the belt. The belt is the geometry of space-time inside the black hole. The geometry says, inward is the future. The singularity is the only destination. The journey from the event horizon to the singularity takes a finite amount of proper time. For a stellar mass black hole, approximately 1 solar mass, the maximum proper time from horizon to singularity is approximately 10 microseconds, 10 millionths of a second. For a supermassive black hole like Sagittarius A star, 4.3 million solar masses, the time is approximately 20 seconds. For M87 star, 6.5 billion solar masses, approximately 8 hours. The infaller has no way to avoid the singularity. The infaller has no way to signal anyone outside. The infaller's experience, whatever it is, whatever the quantum gravity effects near the singularity produce, is permanently hidden behind the event horizon. No signal, no measurement, no information can escape to tell the external universe what happens at the center. This is the part that stays with me. Not the mathematics, though the mathematics is precise and confirmed by every observation. The implication. Inside a black hole, the future is a singularity, a point where the equations end, where the known laws of physics break down, where created physics reaches its boundary. Outside a black hole, we live in a universe where the future is open, where the laws of physics operate predictably, where time flows forward into outcomes that are, at least in principle, calculable. The event horizon is the boundary between these two regimes, between a future governed by known laws and a future that terminates in their breakdown. The infaller crosses this boundary without noticing. The external observer never sees the crossing. Both are right. The universe, the created universe, the universe whose laws were established with the precision we have been examining, permits both descriptions simultaneously. Two realities, one space-time, one set of equations, two irreconcilable experiences. What does it mean that inside a black hole, the singularity is not a place, it is the future? What does it mean that the most inevitable thing inside a black hole is the end of physics itself? Now let us examine what happens to a physical object, a human body for instance, as it falls toward and into a black hole. The answer depends dramatically on the mass of the black hole. And the dependence reveals something counterintuitive. The larger the black hole, the gentler the crossing. Tidal forces, the differential gravitational pull between the near side and far side of an extended object, are the mechanism of destruction near a compact mass. Gravity is not uniform. It pulls harder on the side of your body closer to the black hole than on the side farther away. This differential, the tidal force, stretches you along the radial direction and compresses you along the lateral directions. The effect is called spaghettification, a term popularized by Kip Thorne, born 1940, American physicist, Nobel Prize 2017 for the detection of gravitational waves, scientific consultant for the film Interstellar. The tidal acceleration gradient at the event horizon scales inversely with the square of the mass. The equation is the tidal gradient equals c to the sixth divided by the quantity 2gm all squared. For a stellar mass black hole, approximately 1 solar mass, with a Schwarzschild radius of approximately 3 kilometers, the tidal gradient at the horizon is approximately 10 to the 9th g per meter. That is approximately 2 billion times the acceleration of gravity, applied as a stretching force across each meter of your body length. A human falling toward a stellar mass black hole would be stretched into a thin filament, a thread of atoms pulled to extraordinary length, long before reaching the horizon. The stretching would begin thousands of kilometers from the event horizon. The body would separate at the weakest structural points first, the joints, the cartilage. Then the muscles would tear, the bones would fracture, the cells would separate, the molecules would dissociate, and finally the atoms themselves would be pulled apart. The process would take milliseconds. The result would be a stream of subatomic plasma spiraling inward, stretched thinner than a strand of spider silk, accelerating toward the singularity at velocities approaching the speed of light. Picture this visually. A camera positioned thousands of kilometers from a stellar mass black hole. A dark sphere, approximately 6 kilometers across, approximately 3.7 miles, surrounded by a thin disk of superheated gas, glowing blue-white at the inner edge and orange-red at the outer edge, warped by gravitational lensing into a distorted halo. A probe falls toward the black hole. As the probe enters the tidal zone, it begins to elongate, slowly at first, then rapidly, stretching like taffy pulled by invisible hands. The probe, originally a compact sphere, becomes an ellipsoid, then a cylinder, then a thread, then a filament so thin it is invisible to the camera. The filament spirals inward, joining the accretion disk's inner edge, glowing briefly as friction heats it to millions of degrees, then crossing the horizon and vanishing from the camera's view, freezing, reddening, fading to black. For a supermassive black hole, approximately 1 million solar masses, with a Schwarzschild radius of approximately 3 million kilometers, the tidal gradient at the horizon drops to approximately 0.001 g per meter. This is barely noticeable. An astronaut crossing the event horizon of a million solar mass black hole would feel essentially nothing. No stretching, no compression, no discomfort. The tidal forces would be comparable to the tidal forces you experience right now, sitting on the surface of the Earth due to the Moon's gravity. The crossing would be smooth. The equivalence principle would hold perfectly. Locally, the astronauts' experience would be indistinguishable from floating in empty space, far from any gravitational source. Think about this through an analogy. Picture two rivers flowing toward waterfalls. One river narrows abruptly into a 10-meter-wide gorge before plunging 300 meters straight down. The gradient is extreme, the current lethal, the turbulence visible from kilometers away. The other river widens to 10,000 kilometers before descending the same vertical distance over a continental-scale slope. The gradient is imperceptible, the current gentle. A boat drifting on the surface would notice nothing unusual at any given point. Both rivers carry water downward. Both end at the bottom. The stellar mass black hole is the narrow gorge. The supermassive black hole is the continental slope. The destination is the same, the singularity. The experience is vastly different. This counterintuitive fact that the most massive black holes are the most hospitable at their horizons has a concrete anchor in our own galaxy. Sagittarius A star, the supermassive black hole at the center of the Milky Way, approximately 26,000 light-years from Earth, has a mass of approximately 4.3 million solar masses. Its Schwarzschild diameter is approximately 51.8 million kilometers, approximately 32.2 million miles, roughly one-third the distance from the Earth to the Sun. Its presence was confirmed through decades of painstaking observation, most notably by tracking the orbits of stars in its vicinity. The gravity instrument, a near-infrared interferometer at the Very Large Telescope Interferometer in the Atacama Desert of Chile, measured the orbit of the star S2 as it swung around Sagittarius A star at speeds exceeding 25 million kilometers per hour, approximately 15.5 million miles per hour, roughly 2.5% of the speed of light, at its closest approach of approximately 120 astronomical units. The orbital measurements, combined with those of Reinhard Genzel's team at the Max Planck Institute and Andrea Ghezi's team at UCLA, provided the mass and distance measurements that confirmed Sagittarius A star as a supermassive black hole. Genzel and Ghez shared the 2020 Nobel Prize in Physics with Roger Penrose for this work. The Event Horizon Telescope captured Sagittarius A star's image on May 12, 2022. A glowing ring of superheated gas, orange and gold, surrounding a dark central shadow. The image was harder to produce than the M87 image because Sagittarius A star is approximately 1,500 times lighter than M87 star, which means the gas orbits approximately 1,500 times faster, changing the appearance of the ring on timescales of minutes rather than weeks. The EHT team had to develop new imaging algorithms to account for this rapid variability. The result confirmed general relativity's predictions. The shadow size matched the Schwarzschild radius to within the measurement uncertainty. An astronaut falling into Sagittarius A star would cross the event horizon without noticing. The tidal forces at the horizon, approximately 0.001 g per meter, for a 4.3 million solar mass black hole would be imperceptible. The astronaut would experience minutes of continued freefall inside the horizon before encountering serious tidal stretching. The spaghettification would come. The singularity is inescapable, but the crossing itself would be smooth, quiet, and unremarkable. From Earth, we would never see the astronaut cross. We would see them freeze, redden, fade, their image dimming over years, decades, centuries, until the signal was undetectable. Two descriptions, two realities, one equation. The black hole in Messier 87, M87 star, is approximately 6.5 billion solar masses, approximately 1,500 times more massive than Sagittarius A star, located 55 million light-years from Earth in the constellation Virgo. Its image, released on April 10, 2019, was the first direct image of a black hole's shadow ever produced, a historic achievement requiring the coordination of 8 radio observatories on 4 continents, operating at a wavelength of 1.3 millimeters with a combined angular resolution of approximately 20 micro-arcseconds. The image shows an asymmetric ring, brighter on the southern side, where gas moves toward us and is Doppler boosted, dimmer on the northern side, where gas moves away. The dark center, the shadow, is approximately the size of our entire solar system out to the orbit of Pluto. The Chandra X-ray Observatory, NASA's space-based X-ray telescope, launched in 1999, provided complementary observations of the relativistic jet emerging from M87 star, a beam of charged particles accelerated to near light speed, extending thousands of light-years from the black hole's poles. What does it mean that we have photographed the shadow of an event horizon, the boundary from which nothing escapes, and yet we still do not know what lies inside? On September 14, 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, with detectors in Livingston, Louisiana, and Hanford, Washington, each with 4-kilometer laser arms sensitive to length changes of approximately 10 to the negative 21, detected gravitational waves for the first time. The signal, designated GW150914, was produced by 2 stellar mass black holes, one approximately 36 solar masses and the other approximately 29 solar masses, spiraling into each other and merging 1.3 billion light-years from Earth. The merger produced a final black hole of approximately 62 solar masses, with approximately 3 solar masses converted into gravitational wave energy, radiated outward as ripples in spacetime. The detection confirmed the existence of stellar mass black holes, the reality of gravitational waves, and the predictions of general relativity in the strong field regime. It also confirmed that event horizons are real. The merging objects produced no electromagnetic signal from the merger itself, unlike neutron star mergers, consistent with the prediction that the event horizons swallowed all matter and light. What does it mean that we have directly detected the gravitational waves from merging black holes, confirming that event horizons are real, that general relativity's predictions hold in the most extreme conditions, and yet we still do not know what happens at the singularity? This brings us to the information paradox, and to the specific way in which the event horizon threatens the foundations of quantum mechanics. Stephen Hawking, born 1942, died 2018, British physicist, Lucasian Professor of Mathematics at Cambridge, author of A Brief History of Time, made a discovery in 1974 that transformed black hole physics and opened a wound in the foundations of physics that remains unhealed 50 years later. Hawking applied quantum field theory to the curved space-time around a black hole and showed that the event horizon is not perfectly black. It radiates. The mechanism is rooted in the quantum vacuum, the fact that empty space, even in the absence of all matter and radiation, is not truly empty. The vacuum seethes with virtual particle-antiparticle pairs, created and annihilated in intervals shorter than the Heisenberg uncertainty principle allows permanent existence. Near the event horizon, this process acquires a new dimension. A virtual pair is created just outside the horizon. One particle falls inward, crossing the horizon and becoming real, at the cost of reducing the black hole's mass. The other particle escapes outward, carrying energy away from the black hole as Hawking radiation. The process is slow, faint, and, for astrophysical black holes, currently undetectable. It is also, if the calculation is correct, inevitable. The temperature of Hawking radiation is given by the second equation. T sub h equals h bar c cubed divided by 8 pi g m k sub b. T sub h is the Hawking temperature, the effective temperature of the black hole's thermal glow. H bar is the reduced Planck constant, approximately 1.055 times 10 to the negative 34 joule seconds. C is the speed of light. G is the gravitational constant. M is the black hole's mass. K sub b is Boltzmann's constant, approximately 1.381 times 10 to the negative 23 joules per Kelvin. The equation reveals an inverse relationship. The more massive the black hole, the lower its temperature. A stellar mass black hole, one solar mass, has a Hawking temperature of approximately 10 to the negative 7 Kelvin, 1/10,000,000th of a degree above absolute zero. This is colder than the cosmic microwave background, the thermal relic of the Big Bang, which bathes all of space at approximately 2.725 Kelvin. A stellar mass black hole absorbs more energy from the CMB than it emits as Hawking radiation. It is growing, not shrinking. Only a black hole lighter than approximately 10 to the 22 kilograms, roughly the mass of the Moon, would be hot enough to emit more than it absorbs and begin to evaporate in the current cosmic epoch. Think about this through an analogy. Picture a block of ice in a warm room. The ice absorbs heat from the room and melts. Now picture a block of ice in a room that is colder than the ice. The ice does not melt. It grows as moisture from the air freezes onto its surface. A stellar mass black hole is ice in a room colder than itself. The CMB is warmer, and the black hole absorbs energy. A microscopic black hole, if one existed, would be ice in a blazing furnace. it would evaporate rapidly, radiating energy faster than it absorbs it. The temperature of the room, the CMB, decreases as the universe expands. Eventually, trillions of years from now, the CMB will cool below the Hawking temperature of even stellar mass black holes, and they will begin to evaporate. The process will take approximately 10 to the 67 years for a solar mass black hole. That is 10 followed by 67 zeros, a duration so long that the current age of the universe, approximately 1.38 times 10 to the 10 years, is an insignificant fraction of it. Hawking's discovery had a personal dimension. In 1975, he made a bet with Kip Thorne on whether information is destroyed in black holes. Hawking argued that information is lost, that the thermal nature of Hawking radiation means the specific quantum state of whatever fell in is erased. Thorne agreed with Hawking. John Preskill, American physicist at Caltech, took the opposite side, arguing that information must be preserved because quantum mechanics demands it. In 2004, Hawking conceded the bet, stating that information is not lost but is encoded in the Hawking radiation in a manner consistent with unitarity. He gave Preskill a baseball encyclopedia, symbolizing the information that is preserved. The concession was controversial. Many physicists were not convinced that Hawking had identified the mechanism by which information escapes. The paradox remained. In his later years, Hawking proposed a resolution involving apparent horizons rather than absolute event horizons, surfaces that trap light temporarily but eventually dissipate, allowing information to escape. He stated that the chaotic dynamics near the horizon scramble the information so thoroughly that predicting what will come out is as difficult as predicting the weather. The proposal attracted attention, but did not resolve the paradox to the physics community's satisfaction. What does it mean that the most celebrated result in quantum gravity, Hawking radiation, appears to violate the most fundamental principle of quantum mechanics, unitarity, and that the paradox remains unresolved after 50 years? The problem, the information paradox, is this. Hawking radiation is thermal. It has a black-body spectrum determined only by the black hole's mass, charge, and spin. It carries no information about what fell in. If a book falls into a black hole, the Hawking radiation emitted as the black hole evaporates does not encode the contents of the book. The information in the book, the specific arrangement of letters, the specific sequence of pages, the specific quantum state of every atom, is apparently lost. Quantum mechanics forbids this. Quantum mechanics is unitary. The development of any quantum system preserves information. The future state determines the past state, and vice versa. Information cannot be destroyed. It can be scrambled, hidden, redistributed, but not erased. Think about this through an analogy. Picture a library that burns down. The books are destroyed. The ash contains no readable text. Yet, in principle, in the physics, the information is not lost. If you knew the exact quantum state of every atom in the ash, every photon emitted by the fire, every molecule of smoke, you could reconstruct the books. The information is scrambled but preserved. The total quantum state of the universe after the fire contains the information that the total state before the fire contained. Quantum mechanics guarantees this. Now picture a library that falls into a black hole. The books cross the event horizon. The black hole eventually evaporates into thermal Hawking radiation. The radiation is featureless, a black body spectrum carrying no specific information about the books. The information appears to be erased, not merely scrambled. This is the paradox. Either Hawking radiation secretly encodes the information, in which case the radiation is not truly thermal and Hawking's calculation is incomplete, or information is genuinely lost, in which case quantum mechanics is wrong. Neither option is comfortable. What does it mean that the most celebrated result in quantum gravity, Hawking radiation, appears to violate the most fundamental principle of quantum mechanics, unitarity? This paradox has generated some of the most creative, controversial, and unresolved theoretical physics of the past 50 years. Let us examine the major proposals. Black hole complementarity, proposed by Leonard Susskind, born 1940, American physicist at Stanford, one of the founders of string theory, and colleagues in 1993 to 1994, offers an audacious resolution. Complementarity proposes that no single observer ever witnesses a contradiction. The external observer sees information encoded in the Hawking radiation, scrambled, delayed, dispersed across decades of faint thermal emission, but ultimately recoverable in principle. The infalling observer carries information through the horizon into the interior, where it encounters the singularity. Both descriptions are valid. Neither observer can access both descriptions simultaneously because accessing both would require faster-than-light communication or the ability to be in two places at once. The apparent contradiction arises only if you try to combine the two perspectives into a single global account. And complementarity says you cannot do this. No experiment performed by a single observer reveals a paradox. The contradiction exists only in the mind of the theorist, who attempts to merge perspectives that nature keeps separate. Think about this through an analogy. Picture two security cameras monitoring the same hallway, one pointed east, one pointed west. A person walks through the hallway. Camera east records the person walking from left to right. Camera west records the person walking from right to left. Both recordings are correct. Both describe the same event. Neither recording contradicts the other, unless you insist that left to right and right to left cannot both be true simultaneously. They can, because the two cameras have different perspectives. The apparent contradiction is an artifact of trying to combine two valid viewpoints into a single description. Complementarity says the event horizon works the same way. The infalling and external views are different cameras, and no single camera captures both. Think about it through another analogy. Picture two accountants auditing the same company. One auditor examines the books from the perspective of revenue, money coming in. The other examines the books from the perspective of expenses, money going out. Both auditors produce complete, internally consistent reports. The revenue report shows growth. The expense report shows loss. If you try to combine them naively, without the rules of double-entry bookkeeping, you get a contradiction. With the rules, the contradiction dissolves into a consistent whole. Complementarity proposes that the rules connecting the two perspectives exist, but we do not fully know them. We know the perspectives are consistent because the mathematics guarantees it. We do not know the mechanism that makes them consistent. The prosecution of complementarity. It was widely accepted for nearly 20 years, from 1993 to 2012. It resolved the information paradox elegantly and preserved the equivalence principle at the horizon. It was, in the language of theoretical physics, the standard story. Physicists moved on. The paradox appeared solved. And then, in 2012, 4 physicists shattered the consensus. Ahmed Almheiri, Donald Marov, Joseph Polchinski, born 1954, died 2018, American physicist at the Kavli Institute, one of the great string theorists of his generation, and James Sully, collectively known as AMPS, published a paper that identified a fatal flaw in complementarity's architecture. The AMPS argument, the firewall hypothesis, proceeds through a chain of logical steps, each individually reasonable, whose collective conclusion is devastating. Step 1. Quantum mechanics requires that the late Hawking radiation, emitted near the end of a black hole's life, be entangled with the early Hawking radiation, emitted earlier. This entanglement is necessary for information recovery, for the total radiation to encode the information about what fell in. Step 2. The equivalence principle requires that an infaller crossing the horizon experience nothing unusual, which means the vacuum state near the horizon must be smooth, which requires the late Hawking radiation to be entangled with its interior partner, the particle that fell inward when the pair was created. Step 3. Quantum mechanics forbids a particle from being maximally entangled with 2 different systems simultaneously. This is called monogamy of entanglement. The late Hawking radiation cannot be simultaneously maximally entangled with the early radiation, as required for information recovery, and with the interior partner, as required for a smooth horizon. Something must give. AMPS concluded that the equivalence principle fails at the horizon. Instead of a smooth crossing, the infalling observer encounters a firewall, a curtain of high-energy quanta at the event horizon that destroys anything that touches it. The firewall burns the infaller before they can cross. The interior of the black hole, in the firewall scenario, may not exist at all, or if it exists, it is unreachable. AMPS stated, "A central consequence of our argument is that either the interior of a black hole does not exist, or else that there can be no information-preserving description of black hole evaporation." Think about this through an analogy. Picture a border crossing between 2 countries. Country A guarantees free passage across the border. No checkpoints, no barriers, no delays. Country B guarantees that no smuggled goods can cross. Every item must be inspected and accounted for. The 2 guarantees are compatible when traffic is light. When traffic reaches a critical volume, when the number of items that must be accounted for exceeds the capacity of the border to pass freely, one guarantee must be broken. Either free passage is revoked, a checkpoint is installed, the firewall, or accounting is abandoned, information is lost. You cannot have both at full capacity. The black hole reaches this critical volume approximately halfway through its evaporation, the Page time, named after Don Page, who identified this transition in 1993. At the Page time, complementarity breaks down, and AMPS shows that the choice is between the equivalence principle and unitarity. The firewall is the checkpoint. The loss of information is the abandonment of accounting. Most physicists choose unitarity because quantum mechanics has never been observed to fail, and accept the firewall with all its disturbing implications. Joseph Polchinski, who died of brain cancer in 2018 at the age of 63, spent his final years defending the firewall argument and exploring its consequences. The argument has not been refuted. It has been debated, reinterpreted, modified, and qualified, but the core logical structure stands. The firewall hypothesis remains one of the most important and unsettling results in theoretical physics of the 21st century. What does it mean that preserving the fundamental principles of quantum mechanics may require destroying the fundamental principle of general relativity, the equivalence principle, at the event horizon? What does it mean that the smooth crossing predicted by Einstein's equations for over a century may be replaced at the quantum level by an impenetrable wall of fire? The fuzzball conjecture, proposed by Samir Mathur, born 1960, theoretical physicist at Ohio State University, beginning in the early 2000s, offers a different resolution from string theory. In the fuzzball picture, each black hole microstate has a distinct horizon-scale structure, a fuzzy surface with no interior. There is no singularity. There is no empty interior. The infalling matter does not pass through the horizon into a vast empty space. It is absorbed on the fuzzball surface, which encodes the information in its quantum structure. Every microstate is different. Every black hole has a unique internal configuration. The information is not lost because it was never hidden behind a horizon. It is encoded on the surface. The Bekenstein-Hawking entropy supports the fuzzball picture indirectly and introduces one of the most counterintuitive results in all of physics. The entropy of a black hole, the third equation, S equals K sub B times A divided by 4 times the Planck length squared, is proportional to the horizon area, not the volume. S is the entropy, a measure of the number of microscopic configurations, microstates, consistent with the macroscopic description. K sub B is Boltzmann's constant. A is the area of the event horizon. The Planck length squared, approximately 10 to the negative 70 square meters, sets the fundamental scale. Jacob Bekenstein, born 1947, died 2015, Israeli-American physicist, first proposed in 1973 that black holes carry entropy proportional to their horizon area. The idea was initially met with skepticism. Hawking himself resisted it. If a black hole has entropy, it has a temperature. If it has a temperature, it radiates. In 1974, Hawking calculated the radiation and confirmed Bekenstein's insight. Black holes are thermodynamic objects with temperature, entropy, and the capacity to exchange energy with their surroundings. The numbers are staggering. A solar mass black hole with an event horizon area of approximately 1.1 times 10 to the 8 square meters, approximately 1.2 times 10 to the 9 square feet, has an entropy of approximately 10 to the 77 in units of Boltzmann's constant. For comparison, the entropy of the Sun, a sphere of plasma containing 2 times 10 to the 30 kilograms of matter at millions of degrees, is approximately 10 to the 58. The black hole, which is described by only 3 numbers, mass, charge, and spin, has an entropy 10 to the 19 times larger than the star from which it formed. It appears simple. It is, in information theoretic terms, the most complex object in the universe. Think about this through an analogy. Picture a safe in a bank vault. The safe is described by 3 external measurements: its height, its width, and its depth. Simple, 3 numbers. Now open the safe. Inside are documents, trillions of documents, each different, each containing unique information, each contributing to a total information content that dwarfs the simplicity of the external description. The external description tells you nothing about the contents. The contents are vastly more complex than the container. A black hole is this safe. 3 external numbers: mass, charge, spin. Internal complexity of 10 to the 77 microstates. The simplicity of the exterior conceals a staggering internal richness. What does it mean that a black hole, described by 3 numbers, has more entropy than most of the rest of the observable universe combined? The fact that entropy scales with area, not volume, is one of the central motivations for the holographic principle. The idea, proposed independently by Gerard 't Hooft, born 1946, Dutch physicist, Nobel Prize 1999 for his work on quantum chromodynamics, and Leonard Susskind in the 1990s, that all the information in a 3-dimensional volume can be encoded on its 2-dimensional boundary. The name comes from the analogy to a hologram, a 2-dimensional surface that, when illuminated, projects a 3-dimensional image. The holographic principle proposes that the physical universe works the same way. The 3-dimensional reality we experience may be a projection of information stored on a distant 2-dimensional surface. For black holes, the holographic principle is concrete. The entropy, the information content, is proportional to the horizon area, not the interior volume. The information about everything that fell into the black hole is encoded on the horizon surface at a density of 1 bit per 4 Planck areas. The Planck area, approximately 2.6 times 10 to the negative 70 square meters, is the smallest meaningful unit of area in physics. At this scale, every bit of information about every atom, every photon, every quantum state that crossed the horizon is inscribed on the boundary.
The interior is a projection. Juan Maldacena, born 1968, Argentine theoretical physicist, one of the most cited physicists in history, made the holographic principle mathematically precise in 1997 with the ADS/CFT correspondence. Maldacena proved an exact duality, a gravitational theory in a 5-dimensional anti-de Sitter space, a space-time with a negative cosmological constant, is precisely equivalent to a 4-dimensional conformal field theory, a quantum field theory with no gravity, on its boundary. The 2 theories, one with gravity, one without, describe exactly the same physics. every calculation in one can be translated into a calculation in the other. A black hole in the five-dimensional interior corresponds to a thermal state in the four-dimensional boundary theory. The boundary theory is unitary, information is preserved. Therefore, the bulk theory must also be unitary, even though it contains black holes that appear to destroy information. Maldasena's result does not explain the mechanism by which information escapes the black hole. It proves that information must escape because the boundary theory preserves it, and the boundary theory is equivalent to the bulk. Think about this through an analogy. Picture a novel written in two languages, English and Japanese. The two versions have different grammar, different vocabulary, different sentence structures. The English version tells a story involving a locked room mystery. The Japanese version tells the same story, but in the Japanese version, the mystery is solved. The two versions are exact translations. If the mystery is solved in the Japanese version, it must be solved in the English version, even if the English translation does not make the solution obvious. Maldasena's ADS/CFT is the dictionary between the two languages. The boundary theory is the Japanese version. Information is preserved, the mystery is solved. The bulk theory is the English version. Black holes appear to destroy information, the mystery seems unsolvable. The dictionary guarantees the English version has a solution, even though we have not found it yet. Shinsei Ryu and Tadashi Takayanagi, physicists who, in 2006, proposed a formula that made the holographic connection quantitatively precise, showed that the entanglement entropy of a region in the boundary theory equals the area of a minimal surface in the bulk divided by 4 times Newton's constant. The Ryu-Takayanagi formula connects quantum entanglement, the most fundamental quantum correlation, to geometry, the shape of spacetime. It suggests that spacetime itself may be woven from entanglement. In 2013, Susskind and Maldacena proposed an even more radical connection. ER equals EPR. ER stands for Einstein-Rosen bridges, wormholes, tunnels through spacetime connecting two distant regions. EPR stands for Einstein-Podolsky-Rosen, the quantum entanglement of distant particles, first described in 1935. The ER equals EPR conjecture proposes that every pair of entangled quantum particles is connected by a microscopic wormhole. The wormholes are too small and too short-lived to transmit information. You cannot send a message through them, but they exist as geometrical connections, linking entangled systems across arbitrary distances. If this is correct, then the Hawking radiation emitted by a black hole is connected to the black hole's interior by a network of microscopic wormholes, providing a geometrical channel for information transfer that preserves unitarity without violating the speed of light. The conjecture is speculative. It is unproven. It is extraordinarily creative. And it suggests something deep, that the fabric of space-time itself, the stage on which all physics plays out, is not fundamental. It is emergent. It is woven from quantum entanglement, stitch by stitch, connection by connection, wormhole by microscopic wormhole. If ER equals EPR is correct, then spacetime is not the ground floor of reality.
entanglement is.
Spacetime is the building. Entanglement is the foundation. What does it mean that the leading proposals for resolving the information paradox, complementarity, firewalls, fuzzballs, ER equals EPR, holography, are mutually incompatible? Each requires physics we have not confirmed, and none is accepted by a consensus of physicists. What does it mean that after 50 years, the deepest paradox in theoretical physics, the tension between gravity and quantum mechanics at a black hole's horizon, remains unresolved? Before I continue, consider what this means. Take a moment. The information paradox is not an academic puzzle. It is a confrontation between the two pillars of modern physics, general relativity and quantum mechanics. General relativity says black holes destroy information at the singularity where the equations break down. Quantum mechanics says information cannot be destroyed. Unitarity is sacrosanct. Both theories are confirmed to extraordinary precision in their respective domains. Both cannot be right at the event horizon. Something must give. And after 50 years of effort by the most brilliant theoretical physicists in history, Hawking, Susskind, 't Hooft, Maldacena, Penrose, Thorne, no one has identified what gives. The materialist response to these paradoxes is familiar. Science will eventually explain it. Some physicists propose that a future theory of quantum gravity, perhaps string theory, perhaps loop quantum gravity, perhaps something not yet conceived, will resolve the singularity, explain the information paradox, and close the remaining gaps. The prosecution. This is not an argument. It is faith. Faith in future discoveries deployed to avoid a present conclusion. Physics has been working on the information paradox since the 1970s. 5 decades. No resolution. The singularity has been a known problem since 1965, Penrose's theorem. 6 decades. No resolution. The event horizon paradox, the disconnect between proper time and coordinate time, between the infaller's experience and the external observer's record, has been understood since the 1950s. 7 decades, no resolution. Science will explain it eventually is a promissory note, not a conclusion. It assumes that the explanation will be naturalistic, but the assumption itself is the question at issue. The evidence we have points in a specific direction. Let us follow it. Something has always existed. If there were ever truly nothing, no matter, no energy, no space-time, no laws, no potential, no mathematical structures, then nothing would exist now. Nothing has no mechanism. Nothing has no tendency. Nothing has no creative power. 0 plus 0 equals 0, always, permanently, without exception. The universe exists. Black holes exist. The Schwarzschild radius exists. The event horizon exists. The equations that describe them exist. Something has always existed. The question is what, and whether that something is unconscious matter or an intelligent cause. The universe itself has not always existed. The Big Bang describes the expansion from a singularity, a point of infinite density and 0 volume, approximately 13.8 billion years ago. The evidence is convergent and overwhelming. The cosmic microwave background, detected by Arno Penzias and Robert Wilson at Bell Labs in 1965, mapped by COBE in 1992, WMAP in 2003, and the Planck satellite in 2018, the observed expansion, measured by Edwin Hubble in 1929, confirmed as accelerating by Saul Perlmutter, Brian Schmidt and Adam Rees in 1998, primordial nucleosynthesis, the observed abundances of hydrogen, helium, deuterium and lithium matching predictions to high precision, and the Borde-Guth-Vilenkin theorem, 2003, establishing that any spacetime with average expansion rate greater than 0 is past incomplete. It had a beginning. The Big Bang describes a process, the expansion. It does not explain what caused the expansion. It does not explain why there was a singularity to expand from. It does not explain why there is something rather than nothing. The Penrose singularity theorem connects the Big Bang to black holes directly. Through the Hawking-Penrose theorems, generalizations proved in the late 1960s by Hawking and Penrose together, the mathematical conditions that guarantee singularities inside black holes also guarantee a singularity at the origin of the universe. Both are points where the equations of general relativity predict their own breakdown. Both are boundaries of known physics. Both are places where the created framework of space-time reaches its limit. The equations describe the approach to the singularity with extraordinary precision. The equations do not describe the singularity itself. The map reaches the edge of the continent and shows only ocean. What does it mean that the same mathematics, Einstein's field equations, Penrose's topological methods, predicts both the origin of the cosmos and the endpoint inside every black hole, and breaks down at both? Consider what the evidence demands. The Schwarzschild radius depends on 3 constants, G, C, and M. The Hawking temperature depends on 5, h bar, c, g, m, and k sub b. The Bekenstein-Hawking entropy depends on 4, k sub b, c, h bar, and g through the Planck length. Each equation combines these constants in a specific way to produce a specific physical prediction. If any of these constants were significantly different, if G were stronger or weaker, if C were faster or slower, if H bar were larger or smaller, the entire edifice of black hole physics would change. Stars might not form. If G is too weak, gravitational collapse does not produce stellar cores hot enough for nuclear fusion. Nuclear fusion might not produce heavy elements if the strong nuclear force coupling is outside its narrow range. Black holes might not exist if the mass thresholds for gravitational collapse fall outside the range of stellar remnant masses. The heavy elements required for planets, for chemistry, for the biochemistry of life, carbon, oxygen, iron, nitrogen, are forged in stellar cores and distributed by supernovae. Without stars, no heavy elements. Without heavy elements, no chemistry. Without chemistry, no life. Without life, no conscious beings to derive the Schwarzschild radius, to calculate the Hawking temperature, to discover the information paradox, to stand outside the event horizon and wonder what lies inside. The fine-tuning is not speculative. It is acknowledged by secular scientists with no interest in theistic conclusions. Stephen Hawking, in A Brief History of Time, stated, "The remarkable fact is that the values of these numbers seem to have been very finely adjusted to make possible the development of life." Hawking was not a theist. He was reporting the physics. Fred Hoyle, born 1915, died 2001, British astronomer, the man who coined the term Big Bang, originally as a dismissal, discovered that carbon nucleosynthesis in stars requires a specific nuclear resonance energy level, the Hoyle state, at approximately 7.65 mega-electron volts. Without this resonance, the triple alpha process would produce negligible carbon, and the universe would contain almost none of the element on which all known life is based. Hoyle stated, "A common-sense interpretation of the facts suggests that a super-intellect has monkeyed with physics, as well as with chemistry and biology, and that there are no blind forces worth speaking about in nature. The numbers one calculates from the facts seem to me so overwhelming as to put this conclusion almost beyond question." Paul Davies, British-Australian physicist, Templeton Prize recipient, stated, "There is now broad agreement among physicists and cosmologists that the universe is in several respects fine-tuned for life." Luke Barnes, Australian astrophysicist, co-author of A Fortunate Universe, 2016, documented that fine-tuning is acknowledged by physicists of diverse backgrounds, including those who seek naturalistic explanations. Roger Penrose calculated the probability of the universe's initial entropy state at approximately 1 in 10 to the power of 10 to the 123. He described this as an absurdly tiny volume of phase space. One could not possibly even write the number down in full in the ordinary denary notation. It would be 1 followed by 10 to the 123 successive zeros. This is the most extreme fine-tuning calculation in all of physics. The initial conditions of the Big Bang, the conditions that ultimately determine whether stars form, whether black holes exist, whether carbon is synthesized, whether life arises, are tuned to a precision that defies any concept of chance. Think about this through an analogy. Picture an architect designing a building. The building must support its own weight, withstand earthquakes, channel water, circulate air, conduct electricity, and maintain temperature, all simultaneously, all within narrow tolerances. Change the strength of the foundation by a few percent, and the building collapses. Change the thickness of the insulation by a margin, and the temperature regulation fails. The architect must know the properties of every material, the interactions between every system, the consequences of every specification, and must select the values that, together, produce a functional structure. Now picture a building that is not a building, but a universe, containing 10 to the 80 particles, governed by 4 fundamental forces, producing stars, black holes, heavy elements, chemistry, life, and consciousness. The architect of this universe must have selected the values of the gravitational constant, the speed of light, the Planck constant, the strong nuclear force, the electromagnetic coupling, the cosmological constant, and dozens of other parameters, all within narrow ranges, all simultaneously,
or producing a cosmos that permits the extraordinary structures we observe, from galaxies to neurons. The materialist response is familiar. Some cosmologists propose the multiverse, an infinite ensemble of universes with varied constants, and we observe our values because only they permit observers. The prosecution. The multiverse has zero evidence. It is unfalsifiable. No other universe has been observed, measured, detected, or interacted with. By the standards of the scientific method, observation, experimentation, falsifiability, the multiverse is not science. It is philosophical speculation. Even if infinite universes existed, the mechanism generating them would itself require explanation, its own constants, its own parameters, its own fine-tuning. The multiverse does not eliminate the need for a cause, it multiplies it. Science will eventually explain it. The prosecution, this is not an argument, it is faith. Faith in future discoveries deployed to avoid a present conclusion. Physics has known about the singularity problem since 1965, about the information paradox since the 1970s, about fine-tuning since the 1980s, about the event horizon paradox since the 1950s. Decades of effort by brilliant physicists have not resolved these questions. The evidence for an intelligent cause is present now, in the fine-tuning, in the mathematical precision of the equations, in the extraordinary structure of black hole thermodynamics, in the unexplained applicability of mathematics to physical reality. The evidence for a naturalistic explanation of these features is absent. Eugene Wigner, born 1902, died 1995, Hungarian-American physicist, Nobel Prize 1963, called the applicability of mathematics to physics a wonderful gift which we neither understand nor deserve. The Schwarzschild radius combines G, M, and C into a single expression that defines the boundary of a region from which nothing escapes. The Hawking temperature combines H bar, C, G, M, and K sub B into an expression that predicts a quantum glow from a classical abyss. The Bekenstein-Hawking entropy combines the Planck length, Boltzmann's constant, and the horizon area into an expression that quantifies the information content of a region of space-time. The Ryu-Takayanagi formula connects entanglement entropy to minimal surfaces in the bulk. Each equation is precise. Each is confirmed, directly or indirectly, by observation. None is derived from any deeper theory. Each is a brute fact, a mathematical structure that maps onto physical reality with unreasonable, unexplained, extraordinary precision. Think about this through one more analogy. Picture a locksmith who discovers a key in his workshop, a key he did not carve, whose origin he cannot trace. He tries it in the front door of his shop. It fits. He tries it in the back door. It fits. He tries it in the safe. It fits. He takes it to his neighbor's shop. It fits every lock. He takes it to a lock he has never seen, in a city he has never visited. It fits. The key is universal. It opens every lock. It was not designed by the locksmith. It was not designed for any specific lock. And yet, the match between key and lock is perfect, complete, and inexplicable. The equations of physics are this key. The physical universe is the set of locks.
The match between them, the unreasonable effectiveness of mathematics, is Wigner's gift. And no naturalistic account has explained it. I return to this point often, not because it is comfortable, because it reveals something that naturalism cannot address. The equations are not random. They are not arbitrary. They are not one set among infinite alternatives that happens to work. They are specific. They are interconnected. They are fine-tuned. They describe a universe in which matter can collapse into black holes, in which event horizons can form, in which information can be encoded holographically on two-dimensional surfaces, in which conscious beings can arise and derive the equations and discover the paradoxes and stand outside the event horizon and wonder what lies inside. The precision of this framework, the mathematical architecture that permits black holes, stars, chemistry, life, and consciousness, points not to accident, but to intention. Not to blind mechanism, but to an intelligent cause, with power sufficient to establish the constants, knowledge sufficient to configure them for a universe of this extraordinary complexity, and will sufficient to select this specific configuration from among the vast space of alternatives. The evidence demands specific attributes of this cause. Power sufficient to establish the gravitational constant, the speed of light, the Planck constant, the Boltzmann constant, and the mass thresholds that permit stellar formation, nuclear fusion, heavy element synthesis, and gravitational collapse into black holes. Knowledge sufficient to configure these constants within the narrow ranges that permit chemistry, stars, planets, life, and conscious beings. Will, because a specific configuration was selected. The constants could have been different. They are what they are because something selected them. Selection from alternatives is an act. Acts require agents. Agents that select possess will. The chain of causes must terminate. An infinite regress of dependent causes, each requiring a prior cause, stretching backward without limit, would never reach the present. The universe exists. The equations hold. The constants are fine-tuned. The singularities mark the boundaries of known physics. The information paradox remains unsolved. The event horizon paradox reveals that reality itself is observer-dependent in ways the equations predict but cannot explain. The evidence converges on an intelligent cause, eternal, uncaused, distinct from the creation, that established the laws, configured the constants, and brought into existence a universe in which black holes can form, horizons can persist, information can be encoded, and conscious beings can stand outside the event horizon and ask why any of it exists at all. What does it mean that you can fall into a black hole but you will never arrive? That two equally valid descriptions of the same event produce irreconcilable conclusions? What does it mean that the equations predict a singularity where the laws break down? What does it mean that the information paradox, after 50 years, remains unsolved? What does it mean that the constants governing black holes, gravity, and space-time are fine-tuned to permit the existence of conscious beings who can study them? It means the evidence points one direction, not to purposeless mechanism, not to blind chance, to an intelligent cause with power, knowledge, and will that configured a cosmos in which event horizons exist, in which time dilates, in which information is preserved, in which singularities mark the limits of created physics, and in which conscious beings arise who can stand at the edge of the knowable and recognize the signature of the one who established the boundary. Let me bring this exploration to a close. We began with two clocks, one falling, one watching, and a paradox that has stood at the heart of general relativity for over a century. The falling clock crosses the event horizon in finite proper time, experiencing nothing unusual at the boundary. The equivalence principle guarantees smooth passage. The watching clock records infinite coordinate time, never seeing the crossing. The Schwarzschild metric's coordinate singularity stretches the signal to infinity. Both descriptions are correct. Both are predicted by Einstein's field equations. The paradox is not a failure of the theory, it is the theory. We trace the history from the beginning. Carl Schwarzschild, serving on the Eastern Front of the First World War, solved Einstein's equations for a point mass in 1916 and died 4 months later at 42 of disease contracted at the front. His solution predicted a radius r sub s equals 2gm/c squared, at which escape velocity equals the speed of light. For decades, this radius was misunderstood. Einstein himself believed it represented a physical barrier that nature could not produce. Arthur Eddington introduced coordinate transformations in 1924 that suggested otherwise. Howard Robertson demonstrated in 1939 that proper time to cross the horizon is finite. Georges Lemaitre showed the same independently. David Finkelstein, in a landmark 1958 paper, proved conclusively that the Schwarzschild radius is a one-way membrane, a coordinate singularity, not a physical one, through which matter and light can pass inward but never outward. We examined the true singularity at r equals 0, where curvature becomes infinite, where space-time itself ends. Roger Penrose proved in 1965 that gravitational collapse inevitably produces singularities, that once a trapped surface forms, general relativity guarantees incomplete geodesics. The theorem earned Penrose a share of the 2020 Nobel Prize, alongside Reinhard Genzel and Andrea Ghez, for their observational confirmation of Sagittarius A star. We examined the space-time swap inside the event horizon, the extraordinary fact that inside the black hole, the radial coordinate becomes time-like, and the time coordinate becomes space-like. The singularity is not a place, it is the future, as inevitable as tomorrow, as unavoidable as the passage of time. The journey from horizon to singularity takes approximately 10 microseconds for a solar mass black hole, approximately 20 seconds for Sagittarius A star, approximately 8 hours for M87 star. We examined the tidal forces, the mechanism of spaghettification. We showed that a stellar mass black hole produces a tidal gradient of approximately 10 to the 9th g per meter at the horizon, stretching any extended object into a filament of subatomic plasma. We showed that a supermassive black hole produces approximately 0.001 g per meter, barely noticeable. We grounded the physics in real observations. The EHT image of M87 star, April 10, 2019, approximately 6.5 billion solar masses, 55 million light-years distant, the first direct image of a black hole's shadow. The EHT image of Sagittarius A star, May 12, 2022, approximately 4.3 million solar masses, 26,000 light-years distant. The gravity instrument's tracking of star S2's orbit around Sagittarius A star at 2.5% of the speed of light. The LIGO detection of GW150914, September 14, 2015, two merging stellar mass black holes 1.3 billion light-years away. The Chandra X-ray Observatory's imaging of M87's relativistic jet, and the Nobel Prizes of 2017, Gravitational Waves, and 2020, Penrose, Genzel, Gez. We examined Hawking radiation, Stephen Hawking's 1974 discovery that quantum effects cause black holes to emit thermal radiation at a temperature inversely proportional to their mass. T sub h equals h bar c cubed over 8 pi g m k sub b. We showed that a solar mass black hole radiates at approximately 10 to the negative 7 Kelvin, colder than the cosmic microwave background, and that evaporation takes approximately 10 to the 67 years. We described the Hawking-Preskill-Thorne bet on information loss, Hawking's 2004 concession, and his later proposal involving apparent horizons. We examined the information paradox, the tension between Hawking radiation's thermal character, which appears to erase information, and quantum mechanics' unitarity, which forbids information erasure. We examined every major proposal for resolution. Complementarity, Susskind, 1993. The idea that no single observer sees a contradiction. The Firewall hypothesis, Amps, 2012. The argument that monogamy of entanglement requires a high-energy barrier at the horizon, destroying infalling objects. The Fuzzball conjecture, Mater. The string theory model replacing the horizon with a quantum surface encoding information. The holographic principle, Te Hooft and Susskind. The idea that three-dimensional physics is encoded on two-dimensional boundaries. The ADS/CFT correspondence, Maldacena, 1997. The exact duality proving that bulk gravity with black holes is equivalent to a unitary boundary theory. The ER equals EPR conjecture, Susskind and Maldacena, 2013. The proposal that entanglement and wormholes are the same phenomenon, suggesting space-time emerges from quantum correlations. The Ryu-Takayanagi formula, 2006, connecting entanglement entropy to minimal surfaces in holographic spacetimes. We showed that each proposal is creative, that each addresses the paradox from a different angle, that they are mutually incompatible, and that none has achieved consensus. The information paradox, after 50 years, remains the deepest unsolved problem in theoretical physics, a direct confrontation between general relativity and quantum mechanics at the event horizon. We examined the Bekenstein-Hawking entropy, S equals K sub B times A over 4 Planck lengths squared, showing that a solar mass black hole has entropy of approximately 10 to the 77, vastly exceeding the entropy of the star from which it formed. We showed that entropy scales with area, not volume, motivating the holographic principle, the idea that reality may be a projection from a lower dimensional boundary. We examined the fine-tuning of the constants G, C, h bar, K sub B, the strong nuclear force, the electromagnetic coupling, the cosmological constant, and showed that the specific values of these constants are necessary for stars, nuclear fusion, heavy elements, chemistry, life, consciousness, and the black holes whose properties we have been examining. We cited the admissions of secular scientists, Hawking calling the fine-tuning remarkable, Hoyle calling it evidence of a super-intellect, Davis noting broad agreement on fine-tuning, Barnes documenting its acknowledgement across diverse backgrounds, Penrose calculating the probability of the initial conditions at 1 in 10 to the power of 10 to the 123. Wigner calling the applicability of mathematics a wonderful gift which we neither understand nor deserve. We examined every escape route. The multiverse, zero evidence, unfalsifiable, shifts the problem without solving it. Science will eventually explain it. Faith, not argument, deployed to avoid a present conclusion. 5 decades on the information paradox. 6 decades on the singularity. 7 decades on the event horizon paradox. The gaps are not closing, they are deepening. Every line of evidence converges. The Schwarzschild radius is precise. The Hawking temperature is exact. The Bekenstein-Hawking entropy is proportional to area. The tidal gradient scales inversely with mass squared. The singularity is guaranteed by Penrose's theorem. The information paradox is unresolved. The event horizon paradox reveals that reality is observer-dependent in ways the equations predict but cannot explain. The constants are fine-tuned. The equations are unreasonably effective. The initial conditions are specified to a precision that eliminates chance. The evidence points to an intelligent cause, eternal, uncaused, possessing power, knowledge, and will, that established the laws, configured the constants, and brought into existence a universe in which black holes can form, horizons can persist, information can be encoded holographically, singularities can mark the boundaries of created physics, and conscious beings can stand outside the event horizon and ask why any of it exists at all. The chain of causes must terminate. An infinite regress would never reach the present. Something uncaused, eternal, and intelligent stands at the foundation, not as a placeholder for future science, but as the conclusion the evidence demands when followed honestly. If you found value in this exploration, consider subscribing. It helps these deep dives reach more curious minds. Sleep well tonight, at a safe distance from every event horizon in the observable universe. The equations describe your position with precision, your proper time ticking steadily, your clock running at a rate determined by your distance from the nearest mass, your photons climbing out of the sun's gravitational well with a redshift of 2 parts per million. The black hole's weight, patient, enormous, colder than the cosmic background, encoding on their horizons more information than everything else in the universe combined. The singularity sits at the center of each one, a point where the equations end, where the laws break down, where created physics reaches its boundary. You can fall into a black hole. You will never arrive, not in the eyes of anyone watching. The paradox is the physics is the evidence, and the evidence points one direction. Good night.